Welcome to Chapter 7. In Chapter 7 we're going to be looking at how plasma membranes are constructed and the role that they play in cells. Much of this is going to be review, although you may stumble across some upgraded terminology and perhaps some deeper levels of understanding than you may currently have. Just to give a brief intro on plasma membranes, throughout this you might hear me call them cell membranes, although it should be understood that I use this term generally. Recall that there are other organelles, the mitochondria for instance, that has the same membrane structure. These plasma membranes are selectively permeable within their environment, and this means that some substances, water, ions, nutrients, and waste products, for example, are capable of entering and exiting the cell. It should be mentioned that some substances are able to pass through the plasma membranes easier than others. Really, this just depends on the needs of the cell. So plasma proteins. These are proteins that are embedded within the plasma membrane, and they're one way that substances can enter the cell. This image does a good job illustrating how the structure of something fits the function. We've been talking a lot about structure fitting the function. If we look at the center of the image right here, we can see a hole. And here's our hole right here. This acts as a doorway for select items to pass through. In this image you'll recognize from the text was said to be a protein that allows potassium ions to pass through, or the K+ ion. Tying back to the idea of selective permeability, this protein is specific to potassium ions and it will not allow other substances to walk through the door. In the slide coming up you'll see a better image that shows these proteins extending from the exterior to the interior regions of the cell. So these proteins, they do go all the way through the cell membrane. Here once again we're looking at the phospholipids. The proteins on the previous slide here would be embedded between these phospholipids, going from the top to the bottom, allowing things to pass through. I'm going to touch briefly on the phospholipids, as we've talked about these in previous units. Recall that the phospholipids are glycerol groups attached to two fatty acid tails, forming a hydrophobic region, which is inside here, and a hydrophilic region, which are these heads. They are attracted to water. Likewise, these heads are attracted to water. The hydrophobic tails, they kind of hang out with one another in the interior there. Now, because phospholipids have a region where they're hydrophilic as well as hydrophobic, they're said to be amphipathic. Amphipathic, that just means that they have both charges, the hydrophobic and the hydrophilic. These differences in charges causes phospholipids, as we said, to arrange themselves in the fashion that they do. These properties in the arrangement of the phospholipids cause plasma membranes to arrange themselves in the two layers that we see on the screen in front of us, hence the name a bilayer. You'll probably have heard that before. So the history of the plasma membrane, scientific inquiry. The first images of cell membranes were not taken until the 1950s, I believe. But scientists have been theorizing about cell membranes for a few decades before. This image on the screen once again shows the arrangement of the phospholipids, but it also includes some of those proteins we had talked about a few slides ago. Some of the proteins right here and right here. We can see the proteins extend from one side of the plasma membrane to the other. The other thing I did not mention is that these proteins are also amphipathic. We said that the phospholipids were, but the proteins are as well. This property of the proteins is actually how they are held in place within the membrane. Looking at the image, the hydrophobic regions are they're actually labeled right here and right here. So the hydrophobic regions, they're hanging out with the hydrophobic tails of the phospholipids, so kind of convenient. Now, one way to look at this image is to compare it to a PB&J, as it's layered with two pieces of bread, top and bottom, two pieces of bread, with the PB&J on the inside. This sandwich model actually was proposed by two guys in 1935, Hugh Davison and James Danieli. These guys also proposed that the phospholipid bilayer was layered internally and externally by proteins, not realizing that the proteins were amphipathic. This misunderstanding was made right in the 70s, 1972 to be specific, by Singer and Nicholson, who proposed that the proteins are found only within the bilayer and the hydrophilic regions exposed to water. So we have our hydrophilic regions on the top and the bottom exposed to the water. This creates a fluid mosaic model, which will be discussed in further detail. So the fluid mosaic model is used to describe the plasma membrane. We've seen a bit of the mosaic part on that last slide there, which is a collection of different materials. Although we saw the phospholipids as well as the proteins and those mixed together, there are many other items in that membrane as well. We'll come back to the mosaic part shortly. However, on this slide we're going to focus more on the fluidity of the membrane. A 1970 report by Larry Fry and Michael Edidin discussed how they learned that the proteins in the cell do, in fact, move and are not anchored into one position only within that membrane. Their test illustrated in the picture on our screen right here. They fused two cells together, so in this case a mouse cell and a human cell, to create a hybrid cell. We can also see that the mouse proteins, which are these pink ones, and the human cell proteins right here in the membrane are the blue ones, were marked previous or prior to the hybridization so that they could actually trace and follow the movement of these proteins to prove that they do move around in the cell membrane. They're not anchored straight into the place that they're fixed in. And we can see that over time, looks like a short period of time, actually an hour, that these marked proteins with the tracers have dispersed themselves evenly and completely throughout the cell membrane of this now combined one larger cell from the two previous cells. So this illustrates that the proteins do move, and it helped pave the way for our understanding that the membranes themselves are indeed fluid. So going back to this slide here, this protein, despite the hydrophobic regions, it could slide down this way, or even bounce off into this direction back here, or even come forward in the picture. Once again, continuing on with the fluidity aspect, not only do the proteins move, but the phospholipids themselves can arrange themselves as well. In this image here, we can see the lateral movement between two phospholipids going one way or the other, whether it's top or bottom, going one way or the other. It's quite common, actually occurring a ton of times every single second. What's less common, though, is the flip-flopping, and that would be where the phospholipid on the top flips to the bottom, and now it's down on the bottom part of the membrane. That doesn't occur all that often. Very, very common, or uncommonly, once per month, will a membrane phospholipid go from the top and stay on the bottom. Typically, they belong to one side, top or bottom, and they tend to stay there. Now, one of the really cool adaptive features of cell membranes is their ability to adapt to environmental changes by altering how fluid they are. Recall that phospholipids have two fatty acid tails, and that those fatty acids can either be saturated or unsaturated. Once again, the unsaturated have less hydrogens as a result of having a double bond between two carbons in the chain, and this causes the fatty acid to have a slight bend shape, and we see those going on, and several of these phospholipids bent there, so that indicates that there's going to be a double bond right there, bent right here, so there's going to be a double bond right there between two carbons. So as we can see, moving from the left image to the right one, the fatty acid tails can alter the levels of saturization. I'm not sure if saturization is a word, guys. I probably should have just said saturation. So something to think about is under what temperatures would membranes be more fluid, and under what temperatures would membranes be more viscous. Think about that. The answer may not be as obvious as it seems. So continuing on with fluidity, here we can see cholesterol is embedded within the plasma membrane, which is a steroid. This adds another element to the mosaic aspect of the plasma membrane, but its function is tied to the fluidity part of the title. Cholesterol is a lipid, so it's going to be inside the sandwich of the membrane with the PB&J. Going back to the question I posed on the last slide, at warm temperatures, such as around 100 degrees Fahrenheit, cholesterol restrains the movement of phospholipids, so it's good to have in there. Why would we want the membranes to be less fluid at high temperatures? Conversely, at low temperatures, cholesterol maintains the fluidity of the membrane, preventing it from tight packing. Why is that such an important adaptation? Think about those things. We're going to draw the line right here on this particular section of Chapter 7, and then we'll pick up in Section 2 with some more of the mosaic aspect.